Right, good afternoon, everyone. So as mentioned, I'm going to start talking about accelerating network transformation through innovation in the RAN. So in Intel, we're working to enable 5G end-to-end. So we have the smart devices, we have cloud processing, and then the access and the core networks to transport the data between those two endpoints. And we're aiming towards that virtual software-defined, cloud-optimized network to fully give the benefits of 5G. So I actually work in the access technology space. Specifically, my team is involved in 5G physical layer processing. So why am I at an SDN and NFE conference? Well, we think that you need to push those principles all the way down through the RAN, and that means including to the physical layer and have it virtualized. So today I'm going to talk a bit about the 5G aspects that really make that virtualization of the RAN key, and how we're using the Intel XEON scalable processor to help us to do that. So one of the key parts of 5G is its variability. So beyond the mobile broadband that you get with today's smartphones, we have all these additional use cases. So we have the enterprise use case, so that's offices, shopping malls, smart factories. We might have some smart stadium use cases, and we want to give fans a really great experience, and we want to let them share that over our social media. And then we have kind of various new residential use cases, so fixed wireless access, and then delivering connectivity to underserved rural communities. And they're all kind of a diverse set of use cases with all different requirements. So 5G supports this by introducing that concept of network slicing. And it also introduces 3 new service types. So enhanced mobile broadband, ultra-reliable low latency, and massive IoT. But when it actually comes to how to manage this network, how to reduce the complexity, and how to kind of manage all these different use cases in one network, it's that SDN and NFE that's going to help us to do that. And so from our perspective, that means we think you need to be running that virtualized RAN on off-the-shelf servers. So to show that this is possible, Intel's created a 5G infrastructure reference design. So this diagram up here, it's designed to show everything like an NFE system. So at the bottom, we've got the various hardware components, so networking, Intel Xeon and Atom processors. Then we've got various accelerators, such as FPGAs and storage. And we've got our virtualization environment with a hypervisor. Here we're showing the Intel Nev SDK, which is a series of libraries to help enable edge computing, then orchestration, and then finally we come to our VNFs. So in this diagram here, the whole of the base station functionality, including that physical layer, is just residing in one or more of those VNFs. We might also have VNFs for distributed EPC. We might have VNFs for other kind of edge operations, such as maybe virtual reality. So if I move on to the 5G physical layer, it's been designed to really support those extra diverse set of use cases. And as you might expect with technology generations, it's a lot more computationally intensive than 4G. So what is it about 5G that makes it harder to do than 4G? So first of all, to meet those requirements, we have to have more capacity. So we're having ever-increasing amounts of data being transmitted. And also one of the key things of 5G is we want to give users our cell edge a better experience. So that means we want to get higher throughput to those cell edge users. So there's a couple of physical layer techniques that we can do to help us. So they're beamforming a massive MIMO. And when we implement these, we need to have sophisticated floating point signal processing functions to enable us to do that. So in the past, a base station could do lots of its processing either integer or fixed point, which is easier. But now we need to introduce floating point to get these more sophisticated techniques and really make better use of our spectrum. Then we've got increased bandwidth. So 5G is due to work across a wider range of frequencies, including millimeter wave. And when we come to millimeter wave, there's more spectrum available up above there. And that means we can have larger channel bandwidths for our cell, which all translates into the fact that we have to process more data. And finally, we come to low latency. So that means the turnaround time we want from our device through our radio access network to some edge cloud processing and returned again, we need that to happen faster. And so at the physical layer, we have to compute all our results faster than we did previously. So I'm going to explain a bit about the XEON scalable processor. We're using this in our work, And it turns out that a lot of the features that it's introduced are key to, are really very beneficial for 5G and key to what we're doing. So some of the things that it's introduced are the AVX512 instruction set. So this is a comprehensive extension to the existing AVX2 vector instruction set. It's also got improvements to cache hierarchy, so that gives us wider bandwidth and it gives us low latency. And we also have improved microarchitecture. So the inner workings of the process has been refined and it results in us having more instructions per cycle. So it's really a combination of features that we're using successfully on 5G. So I'm going to go into just one of these physical layer functions in more depth to try and sort of show how we're using those features and why it's been successful for us. So the one I've chosen is a polar decoder. So this is essentially, it's an error correcting code, and that really just means that you get noisy data coming in, and then we get corrected and we get a clean signal coming out again. So error correcting codes are typically one of the hardest parts of the physical layer to do, and it's something that you would normally offload to an accelerator such as an FPGA or maybe some custom IP. There's various types of error correcting codes within the 5G physical layer. There's something called the LDPC, and that's used on the data channel, so that's the highest throughput we have to process. This polar decoder is used on the control channel. So that is a lower throughput than the data channel, but it's still something you typically do in a hardware accelerator. So I've got a block of data here. So this is called a list 4 decoder, and that just means that my block of data is 4 elements high. We also end up processing things on messages. So here we've got a message with bits running from left to right. So this block of data is kind of one message, and then there's 4 different possible outcomes that it could be. So how do we use the AVX512 instruction set? Well, first of all, it's got 2 times compute, and it's got wider registers, and it's got more registers. In fact, AVX512 means that we're now doing all our instructions on 512 bits, whereas previously it used to be 256 bits. And what that really basically means is the yellow block on that left is bigger than it used to be, so we can process more data in one go. Then it also introduces a concept of registers. And that allows us to perform operations on just a selected group of that data. So I've got grey blocks and blue blocks up here. So say the grey blocks might represent bit 0 and the blue blocks bit 1. And it turns out that quite a lot of operations we would want to do something different based on whether we have a 0 or 1. So maybe the grey blocks we want to do additions, and the blue blocks we want to do 1. And if we use these mask registers, we can do that, make that selection combined with the instruction, whereas previously we had to do some offline logic to actually be able to do that masking. Then it's also got some new instructions. It can be from bit manipulation to more sophisticated floating point operations. And that means that operations that previously used to take 3 or 4 instructions, we can now do in 1. And then finally, these blocks on the right-hand side, the yellow ones are horizontal and vertical. They show that we've got improvement for moving data between lanes and across lanes. And again, that's something we quite often want to do in our processing. So what this means for the polar decoder is that previously it used to be a block that you'd expect to be in hardware, and we can now actually make that recommendation that you should be able to do it in software on the XEON scalable processor. And I should add that I could put up a diagram like this for many of the physical layer functions and just pull out lots of little parts of the AVX512 instruction set that we're able to use to really improve our processing capabilities. So if I kind of take a step back up again and look at network slicing. So network slicing allows mobile operators to put different types of services in slices or give a customer-specific slice. It's not a requirement that those slices have all got unique or challenging requirements, but sometimes they will. So I've just kind of pulled up 4 different slices here. So we have the wireless broadband slice or the smartphone slice. So this is kind of represented by ever-increasing amounts of data. Then I've got a real-time control slice. So it could be automated driving, could be some kind of factory automation. And that really needs ultra-low latency. An IoT or sensor slice. So we've got kind of agricultural monitoring here. It could be smart city. and that's represented by having an increased density of devices. And then finally, a video streaming slice. So you'd expect to get lots of video in your mobile, your wireless broadband slice, but there'll be some videos, such as maybe VR, that's got special requirements, so it might need low latency and it'll be extra high bandwidth. And so slicing is what can enable us to support all these different types. So network slicing is very well defined in the core network. In the access network, it's a lot less clear because ultimately all the data gets sent across that one air interface. And so in the access network, it is quite often used interchangeably with those service types of enhanced mobile broadband, ultra-reliable, low latency, and massive IoT. So I'm going to pull out a couple of examples to just really talk through that slicing and service type and why fully virtualized RAN will help us. So the example I've got up here is an enterprise example, so industrial control. So this might be a private network, which means that it is pretty much just one slice. But it does have different data types inside it. So I've got a video data type here and some kind of industrial control. So if we start off by looking at the video, that could be 8 times 4K video cameras that's sending their data to the RAN and then being routed at the edge compute to a remote control center for monitoring. So that's got the characteristics of more uplink throughput because we're trying to stream video and not particularly stringent latency requirements. But by itself, it's already quite different from wireless broadband data because most of that wireless broadband today is downlink data dominated. So 5G in a TDD system does give us the ability to switch between downlink and uplink subframes based on the amount of data that we have in each direction. But we can also make changes to the physical layer functions to help us. So typically, we could choose particular uplink receive algorithms that would make our uplink throughput more efficient and potentially get another camera inside our cell. So it's kind of worth saying that if you're a base station physical layer designer, then you usually pick all the algorithms that you're going to use, in particular those uplink receive algorithms, based on things like your radio environment, based on the kind of traffic flow that you're expecting to get, and then do trade-offs between cost and performance. So if you're building something for a wide area network, then you want to choose quite generalized algorithms to suit quite a wide range of use cases and have all your base stations the same. But this industrial control is a specific scenario, and it's quite different. So we might want to choose different algorithms to get the best performance out of this scenario. And that's obviously simpler if we're running it virtualized on general purpose compute, because we can use all the processing power that general purpose compute is the same, whereas for kind of custom hardware, you've normally got a mix of processors, DSPs, and FP chain hardware blocks. So you're obviously more constrained in how you can reallocate those resources. So if I move on to that industrial automation at the bottom, so this is really a classical ultra-reliable low latency service type. We would typically send data to the RAN. We'd have to have that processing in the edge cloud because of latency reasons, and then it would get returned back to the automated device. So it's got very tight latency requirements. It's also got quite low throughput. So in this example here, that 50 megabits per second might actually take 50 to 100 devices to actually generate it. It actually turns out from a physical layer perspective that it's the ultra reliability that's the hard part to do. So again, there are particular algorithms we can select in our receive chain that improve that reliability, or we can use a technique which is called transmit diversity, and that's where this device, its signals received by multiple cells, and then those cells are routed back to be processed in one location within the factory. And that turns out to greatly improve the reliability that we get. And obviously, if you're going to route something back to one location and start processing 3 cells at once, that's different from individually processing the cells. So again, having that virtualization is quite key in enabling us to do that. So I was just going to give a second example, which is a smart venue or smart stadium example. So this So smart stadiums are good examples of ultra-dense networks. So ultra-dense networks, when we're having this high density of cells, they work better if you have a lot of coordination between those cells. So this is really a classical example of where it's good to have many cells surrounding your stadium, but to actually pull back as much of the processing as possible to some central location in that stadium. It's also an example. It's also an example with lots of network slicing. So to give every fan a good experience, you might want to have some kind of neutral host example so that all the different operators have got signals within that stadium, and you might want to have a slice that's reserved just for that stadium functions. So the kind of data that we'd have would be operational efficiency data, so smart lighting, smart parking, HVAC systems. You might want some revenue maximization through customized advertising. And then finally, at the bottom, fan experience. So today, a lot of that fan experience is really about sharing your experience up on social media. So you get quite uplink-dominated data within this kind of smart stadium. But going forward, we really want to look to shift that to have a kind of more immersive experience. So maybe some kind of VR system and let the fans get playbacks from multiple angles. So we'd end up switching to a downlink-dominated data system. So again here, the view is that if we have a virtualized RAN, we can transition better over time as we can allocate resources between the amount of uplink data we're getting and the amount of downlink data that we're getting. So really, just to finish in summary, the view is that 5G use cases, they're diverse already. They're not going to remain static, but they will evolve over time. And actually, the work we've been doing to try and virtualize that physical layer and the whole RAN on Intel Xeon scalable processors, we think is key to trying to make sure that 5G can live up to everything that it's promised. So I think I have some time for questions. Hi.
In this example, you just had the stadium. You mentioned there would be multiple slices. What's the situation regarding the scheduling of these 4 slices? How do you envision? Can you control the scheduling? Who gets priority?
So network slicing is it typically is done by a variance of the service level agreements. So and there's several different ways that you can do it. You can ultimately the schedule, if you're going to do them as one individual cell, it just comes down to how you set up that quality of service requirements for different UEs within the scheduler. We have yes. So there's actually talk later on a neutral host. About you, okay. Are you going to? Yeah, I said, yes. My example is, so we work on the physical layer processing, but obviously if you're going to have the expectation is there'll be a neutral host with having that the different individual slices. But we're not working in the area of how we're going to actually schedule. My group's not working in that area of the scheduling of the neutral host. But we, and you expect that it's a service level agreement that gets fed down into the scheduler, and the scheduler can either decide to do a top level of slicing, or it can decide to just translate that into the different quality of services for the different radio barriers or even the different UEs. Yeah. Yeah. Okay. Yeah. Any other questions? Oh.